Okay, and now we move on to the second presentation of the morning session, and this is going to be the final lecture by Filippo Camilloni on his course on electromagnetic fields around black holes. And Filippo, the stage is yours.
Thank you very much, and thanks for you for coming to the final lecture. So just a very quick recap of one of the most important things that we have seen yesterday. It was the valve solution. So it's an electromagnetic vacuum field solely generated by the isometries of the background space-time. And what we learned is basically, one of the most important things that we learned is basically that because of the strong gravitational field of the black hole, which manifests in terms of its spin, we can have the magnetic field lines become twisted and they automatically generate a gravitationally induced electric field. This is something to keep in mind. So, this is a vacuum solution, like we said before. It's, we said yesterday actually, it is actually an unstable solution in the sense that since we have on screen the electric fields, particles will be accelerated and we will have their production, so that in the end we fill the environment around the black hole with a plasma. So in the first lecture I showed you what is the general theory which describes the long distance dynamics, the macroscopic, the hydrodynamic regime for thermal degrees of freedoms, so fluids, and coupled with magnetic fields. This is the theory of relativistic magnetohydrodynamics. Actually, we consider the ideal limit, so ideal MHD, so that everything which is a dissipative effect and contributes to the production of entropy will enter as some correction in a derivative expansion, so in this kind of field theory approach. But what is important to remember here is that we can write the concept quantities of the system, which are these three basically, solely in terms of quantities related to the fluid, so let's say the fluid for velocity and the magnetic field. We can construct equilibrium solutions, but this actually is not really equilibrium. I will explain this in a second. But what I mean is stationary solution. And one of the stationary solutions that were found to be valid around a Kerr black hole is the so-called Commissar of torus, which you can see here. This is the density profile of the torus. And is a stationary solution which is often used to initialize, it's an analytic solution, first of all. And it is often used to initialize the simulations which have to deal with accretion processes. So the ideal is a bit illustrated by this cartoon, which I made. So we can imagine the environment around astrophysical black hole as characterized by a certain accretion disk. This can be very big, very large, as in this case, but can also be very thin. There are different accretion regions, actually, that we can consider. So in this region, basically, the good description is that given by ideal MHD. Now we can initialize the data of a simulation precisely with this Commissar of torus, which is basically a solution in which we assume stationarity, axisymmetry. The magnetic field is present, but is only toroidal, in the sense that it is azimuthal and entering the plane of the spring, and we have constant angular momentum, so that these lines that I draw here are basically the equipotential lines in which the fluid is confined. So when we start with this magnetized torus around the black hole, which is a sort of representation of the accretion disk, then we can introduce some kind of perturbation. We perturb the magnetic field inside the torus. This actually causes the torus to go towards some instability, in particular the magnetorotational instability. And this is why the torus is actually a non-equilibrium solution. It's a stationary but non-equilibrium. It can be perturbed, and this perturbation generates a big mess. So basically we start with this magnetorotational instability. We introduce some turbulent effect. We introduce an effective viscosity, and since we have a viscous flow, it will start the accretion process. So matter will start flowing inside the black hole. And when we reach this stage, which is a simulation done with Bach, basically we are in a turbulent regime where we can also add some resistive effects. So we are basically deviating from the ideal MHD scenario. So this was just to mention that there is a region around the black hole in which MHD is very important to be considered. And in this case are all the processes related to accretion. But actually, here we are interested in more in the regions, in this funnel region, in which the magnetic field is dominant over the plasma. So this is the region where we have the emission of the relativistic jet, and when the Blanford-Snijek mechanism is active. And this region will be described by a limit of magnetohydrodynamics, which is called force-free electrodynamics, and which I mentioned during the first lecture. So the starting point to derive force-free electrodynamics is exactly what I told you. So we consider a regime in which the electromagnetic contribution to the energy momentum tensor is way bigger than the matter contribution, than the fluid contribution. Under this assumption, basically we can neglect the Lorentz force. So it's like if the field is so intense that it completely overwhelms the plasma in the energy and momentum balance, so that every exchange of energy and momentum from the perspective of the field doesn't really matter. So we can neglect the Lorentz force, and when we substitute, here there's different notation, but when we substitute the non-homogeneous Maxwell equation in this equation, what we obtain are the equations of motions of force-free electrodynamics, which can also be considered an independent theory from MHD. And if you look at these equations, it's kind of interesting because this is an electrodynamic regime in which only the tensor F mu, the Faraday tensor, appears. So the electromagnetic field is the only dynamical object in this region. The matter is still present, and it is very important that it's still present because the plasma serves to sustain the magnetic field and to screen all the longitudinal components of the electric fields. So it is very important to remember that force-free electrodynamics is different from vacuum. In both cases, the dynamical quantities are electromagnetic fields, but this is a different regime. It's a sort of zero temperature limit of MHD in which we neglect the thermal degrees of freedom, so the fluid. And as you can see from this equation in particular, this regime becomes highly nonlinear because we have a field appearing together with its derivative. And it's already difficult as it is, so you can imagine how difficult it becomes if we put this equation in a curved background such as the Kerr geometry. And indeed, no exact solution has ever been found for this system of equation, which is also physically relevant. And with physically relevant, I mean that it must be the system must be deterministic and closed, and this can only happen if we have a field in the magnetically dominated region. So I've done this slide, which will be a bit messy in a second, but I'm trying to here illustrate some interesting properties of force-free electrodynamics, which is, in my opinion, a very fascinating theory. So it is useful to rephrase this invariant statement in the Minkowski space-time because it is more clear, and basically this gives you 4 equations which are represented by this, and what we can do now is to take this equation and multiply do a scalar multiplication with the magnetic field. Of course, this term will not contribute because these are orthogonal objects, and what we obtain is that the electric field is automatically orthogonal to the magnetic field. So just because we impose the force-free condition here, we automatically obtain that the field must be degenerate, which is the kind of fields that we want. It means that the plasma is present and it's screening the electric fields. Now, it is also useful sometimes to refer to physical observers, and we can consider a zero angular momentum observer in this case, and consider which is also the normal observer, which I introduced in the previous lectures, and we can also introduce the field that this observer will measure. So, as we can see from this condition, degeneracy implies that these two fields are always perpendicular to each other. But we can also use the anti-symmetry of the Faraday tensor here, and we will notice that these fields, the electric and the magnetic field, are also orthogonal to the forward velocity of the zero angular momentum observer. So what we obtain here is a set of 3 orthogonal vectors. One is time-like, by definition, because we are talking about an observer. 2, a space-like, by construction. And once we have 3 orthogonal 4 vectors, we can always construct a 4th orthogonal 4 vectors. So that we can actually construct an entire set, a basis to describe, which introduce new coordinates to describe the physical objects that we need, for instance. So in these coordinates we have that the ZAMO observer defines a time direction, then the electric and magnetic field defines 2 orthogonal directions, and we can construct a 4th by means of by a contraction with the Levicino tensor. This is useful because if we now look again at the if we now look again at the force-free condition, we can multiply it we can contract it with the zero angular momentum observer, and notice that also the current is orthogonal to the electric field. And this is important because it gives us an idea of how to write the current in an invariant form. Because we know that this current can be decomposed in terms of these orthogonal 4 vectors, but it shouldn't contain any dependence on x, because it must be orthogonal to the electric field. So this is the most general decomposition of the current in force-free electrodynamics, and it is useful to check what are the components of the current which are orthogonal and parallel to the magnetic field. And here we notice something interesting, namely that both of these components, by construction, are dependent on 1 over the square modulus of B. So this is an example that I show to let you understand how it is important that the field is magnetically dominated. Because if it is magnetically dominated, we cannot cancel the magnetic field, which means that you can always write the current in terms of the field, and which means that this condition can only be consistent with a magnetically dominated field, which is also, by construction, degenerate. So these are the two important properties of force-free electrodynamics. And actually, while this is guaranteed by the force-free condition, this is a consistency check that we need to perform every time we derive a solution. This is not automatically guaranteed. Another interesting property is that the degeneracy condition can be written in various different ways, and this implies some interesting mathematical properties, because if we combine these different definitions altogether with the Bianchi identity, which here is written in a differential form way, we basically find that every force-free or degenerate field can be written in terms of the wedge product of two exact differentials, where the two scalars, lambda 1 and lambda 2, are called Euler potentials, and basically represent two coordinates which are orthogonal to the field sheet, which is spread by the motion of the magnetic field line in the space-time. What I'm saying is that, for instance, we can consider a monopolar field, a monopolar magnetic field in cos-t space-time. These two objects, cosine of theta and phi minus omega t minus r, these are the two Euler potential and are perfectly orthogonal to the field, these which are called field sheets, which are submanifolds of the surrounding space-time. And this is, everything is implied by the degeneracy condition. And one can also check what is the induced metric over this submanifolds over the field sheet, and apparently it seems that the induced metric becomes, in this specific case at least, becomes a de Sitter space-time in which the cosmological horizon, given by the Hubble constant, is proportional to the angular velocity of the magnetic field lines, basically. So the fact that the magnetic field lines are rotating, this is our rotating split monopole, basically defines that it exists a surface in which the rotation becomes superluminal. And from the point of view of an observer, which is confined in the field sheet, that acts as a cosmological horizon. You can also generalize this to the case of a background black hole space-time, and you will have two horizons. So this becomes the de Sitter Schwarzschild black hole, for instance. So this was just some interesting properties which I thought it was good to implement, because this kind of discussions were somehow discussed during this symposium. But let's go a bit deeper in force-free electrodynamics applied to the study of magnetospheres. So these are our equations of motions. Actually, there is some very good theorem that tells us that even if we don't know what is the exact form of a solution in the Kerr geometry, we can always decompose, we can always write the field strength in terms of three physical quantities, the one you read. And each of these quantities has a proper physical interpretation. So for example, psi represents the magnetic flux around the horizon, which is constant on the colloidal projection of the magnetic field line. Sorry, maybe it's better if I show this, which are, again, the ZAMO, the field measured by the ZAMO, which, as you can see here, are written explicitly in agreement with this expression. And we see that the magnetic flux here, this psi function, is related to the colloidal component of the magnetic fields, R and theta. I is called the colloidal current, and by means of the Ampere law is related to to the toroidal component. So basically, it is the current flowing through this loop, and so it is related to the azimuthal component of the magnetic fields. And finally, we have another interesting object, which I already mentioned before, which is the angular velocity of the magnetic field lines. So the magnetic field lines in the force-free regime rotate around the black hole as if they were a rigid body, characterized by a certain angular velocity omega. And the lesson that we learned from the Ball solution is that if the magnetic field lines rotate, either because there is an intrinsic rotation of them or because there is a frame dragging effect, we generate an electric field. And indeed, if we write the electric field for this case, we can notice that, first of all, it is by construction orthogonal to the magnetic field, and this velocity, which is the velocity of the field lines, is precisely proportional to the electric field. So this is the, let's say, physical decomposition of a force-free magnetosphere. Now, we have basically that the force-free system of equations give you a relation, a unique relation actually, amongst three different physical variables. And this unique relation is called the Grad-Shafranov equation, which here is written in the Kerr metric, and which is kind of a messy equation. It is a quasi-nonlinear second-order partial differential equation. It's kind of complicated, and the thing which is even more complicated is that we have one single equation, but three field variables to determine. So the only way of solving a magnetospheric problem, which means finding an explicit functional expression for these three objects, is to study this differential equation deeply and understanding that there are critical surfaces. So the differential equation in some point of the space-time will change its character. It will become a first-order equation. So when we have critical points, we have to guarantee that the solution is continuous and the derivatives are continuous. This is not automatically implied by the equation, which admits, because of its critical surfaces, discontinuous solutions. So the way of solving a magnetospheric problem basically consists in solving the stream equation somehow and imposing a certain set of regularity conditions at the critical surfaces of this equation, which in the black hole space-time, in our spinning black hole space-time, are four. So we have, of course, the two critical surfaces are the event horizon and the infinity. So the asymptotic region, R, which goes to infinity. Here is actually, on both these regions, is actually not guaranteed that the fields remain finite. We have to impose this condition. We have to require that the fields remain finite, and in particular, for example, at the event horizon, this is not implied for the azimuthal component of the magnetic field. So that if you ask that an observer, which is freely falling through the black hole horizon, will always measure a finite azimuthal component of the magnetic field, you derive this important relation, also called Snarek condition. There is an analogous relation to for the infinity. So these are two equations which combined together and are only applied in these two regions will allow us to determine the colloidal current I. It's important also to remember that these are not boundary conditions. There was a lot of discussion in the literature about this because with the membrane paradigm it was thought that this naive condition was actually a boundary condition that we set on this membrane which encapsulates the horizon. Actually, it's not. A boundary condition is something which is independent by the equations of motion, and that we have to set to decide which kind of solution we choose we select from this equation. The regularity conditions here are instead regularity conditions which comes directly from the equation. If you evaluate the Grad-Schaffranov equation at the horizon, you will get automatically this condition that guarantees that the field remains finite. Then we have two other critical surfaces which are solidly related to the fact that the magnetic field lines are rotating around the black hole. Since, as I told you before, these behave as rigid bodies, there are 2 points in which the rotations of these magnetic field lines become superluminal. And these are called the light surfaces. We have an outer light surface. This is present even in the non-relativistic regime. For instance, we have an outer light surface also in pulsar magnetospheres, whereas the inner light surface is a characteristic which is only for spinning black holes, and is always confined inside the ergosphere of the black hole. So you might ask, okay, what does it mean that the rotation of the magnetic field lines becomes superluminal? It just means that the particles cannot corrotate together with them. They must acquire, they not simply corrotate. Here, it's forbidden to have just an azimuthal component of the forward velocity. They must acquire some radial direction. So, and the light surfaces are also critical surfaces of the Grad-Schaffranov equation, so that we must impose some regularity condition which guarantees that the magnetic field lines will pass smoothly across them, so that this is imposed by means of this reduced stream equation. I will not go into the derivation because it's not particularly highlighting. So, at this point, we know what are the equations of motions that we need to solve, and we still need to understand how the Blunt-Forsythe mechanism of energy extraction works. Here I would like to show you some argument which illustrates how the Blunt-Forsythe mechanism is actually related to a generalized Penrose process, like we discussed in the first lecture. So, in this case, it is quite useful to consider force-free electrodynamics as a limit of MHD, of magnetohydrodynamics. So magnetohydrodynamics, we both have the matter and the electromagnetic component. When we pass in the force-free regime, basically we only keep the electromagnetic term. And if you consider the energy momentum tensor that I showed you before for MHD, and you neglect all the thermal degrees of freedom, what you are left with is this object. As we've said, from a concept energy momentum tensor, we can always construct another current associated to a Killing vector. And this is, in particular, this is associated to the timeline Killing vector, so that the another current basically represents the electromagnetic momentum associated to a force-free field. And when we look at the absolute value of this electromagnetic momentum, we discover that it is proportional to the GTT component of the metric. Now, you can remember that the ergosphere, which is the region where we can have negative injection of energy at the horizon, is precisely characterized by GTT equals 0. And within the ergosphere, we have GTT greater than 0. So this illustrates that basically a force-free magnetic field acquires negative electromagnetic momentum only inside the ergosphere. And this is an illustration of how we can have negative energies in this in an electromagnetic scenario. But we also derived some useful formulas in our discussion about the generalized Penrose process, which are useful when we are in the continuous regime. So we have some formula relating the power injected into the horizon and the angular momentum rate injected in the horizon in terms of the energy momentum tensor. And for force-free field, these energy momentum tensor components are solidly written in terms of the magnetic spheric field variables, which are basically this. So that what we obtain are two expressions for the energy and angular momentum rate injected at the event horizon. And what we can find is that these energies, these powers, for instance, they basically travel along the curves of constant magnetic flux, which are precisely the poloidal magnetic field lines. So what I'm saying is that this integral is performed where psi is constant. So whenever we have a magnetic field line penetrating the horizon, some kind of power related to the Blunt-Forrest-Nyack mechanism is injected to the horizon by that magnetic field line. In particular, now we can evaluate this integral, or we can write it in a different way, at least, by using the Nyack condition, so the regularity condition at the horizon, which allows us to write an explicit form for I at the event horizon. And we obtain this formula, which is quite illustrative, I will say. First of all, because it shows that if you want to have extraction of energy, so if you want to feed a black hole with negative energy, the field lines must rotate at a lower rate compared to the angular velocity of the black hole. And this is the reason why people started thinking about the membrane paradigm and about the fact that whenever you have a magnetic field line penetrating the horizon, you create some kind of torque. Because you can imagine that this is related, the fact that the angular velocity is lower than that of the black hole is actually related to some sort of inertia that the magnetic field lines hold. And being inertial objects, they tend to slow down the black hole rotation in a sense. Of course, if the magnetic field lines are not spinning, or if the black hole is spinning, this object is automatically zero, and you cannot extract any form of energy. Finally, it is kind of interesting to use this formula and notice that if omega is bound by the angular velocity of the black hole, then there is inequalities between the power injected at the horizon and the angular momentum injected at the horizon, which is this kind of inequality. And this inequality is perfectly consistent with the second law of black hole thermodynamics. You just have to assume that the differential of the mass is related to the energy that you are injecting, and the variation of the black hole angular momentum is related to the angular momentum that you inject. In this case, you will obtain precisely a formula of this type, which is consistent with the idea that a black hole area can always, only increase its value. So here is pretty much how the Blunt-Forrest-Nyack energy extraction mechanism works. Now we have to construct a consistent example which shows that this mechanism can indeed operate. And to construct an example, we need to solve the equations of motion, the Graf-Schaffernoff equation, which is very complicated in general, as I said before. But what we can do is to resort to some perturbative approach. And this was the approach that was originally used by Blunt-Forrest-Nyack in 1977 when they discovered this mechanism. So the idea is that we consider a black hole in the slow spinning regime. And at the leading order, this black hole will look like the Schwarzschild black hole. So around the Schwarzschild black hole, we can always construct vacuum solutions. We have seen some examples in the previous lectures. And in particular, we assume that we have some magnetic field line, some magnetic flux. The black hole is not spinning, so there is no reason to think that there will be some intrinsic angular velocity of the magnetic field line, because what we want is that the magnetic field line will spin because the black hole is spinning. And for instance, the simplest solution you can choose is the one that I illustrated yesterday, the so-called split monopole solution. So a purely radial distribution of the magnetic field line, which is reverse ensign across the equator, which will develop a current shift, which in a sense we can consider like a thin accretion disk that sustain the presence of the electromagnetic field. And this solution is quite useful also because it's very simple. So at this point what we have is a black hole immersed in a monopolar magnetic field. But both the black hole and the magnetic fields are static, and of course we cannot extract any form of energy. So what we can do now is to let the black hole spin and drop into the spinning motion also the magnetosphere. So this essentially means that we are perturbing around the split monopole configuration. We are adding perturbative correction in the small black hole spin to each one of the magnetospheric field variables. And at this point we can solve order by order in the perturbation theory the Grad-Schaffernov equation, which will take the form of a differential operator, the same that I introduced yesterday for the magnetic case, sourced by a certain term, so that every component of this perturbative expansion can be written in terms of the angular eigenfunctions that I introduced yesterday, and some radial term that will take into account the presence of this source. Of course, we also have the various regularity conditions that we should use. At the leading order, which is the one that we are interested in for the moment, we actually don't need to consider the light surfaces. We just need the two Snellian conditions at the event horizon and at the infinity. These are sufficient for solve the magnetospheric problem at the leading order in the case of a split monopole configuration. And you will obtain, like by means of direct substitution of this function psi in here, two expressions for the leading terms of this perturbative expansion, which can be rewritten in this manner in terms of the black hole angular velocity. And it's quite interesting to notice that the angular velocity at the leading order, which a split monopole configuration acquires, is half of the velocity of the black hole, which is, let me come back for a second, which is also the angular velocity which maximizes this integral. So the split monopole configuration is actually very relevant, also because it maximizes the extraction of the energy operated by the Blandford-Snellian mechanism. And once we have the magnetospheric field variables, well, it's done. We just need, sorry, I made some mistake with the animations here. Okay, let's do everything. So once we have the explicit expression for the magnetospheric field variables, what we need to do is simply plug these expressions into the energy extraction formula, which will be minus the energy emitted in the Blandford-Snellian mechanism. Because of course, the negative energy that we inject into the black hole is the positive energy that we gain back, and that will be launched in the jet. And what we find is that this expression at the leading order becomes this quantity. So here we have square dependence on the magnetic flux at the event horizon. This is to be expected because the more magnetic field lines we have threading the horizon, and the more energy we will be able to extract, because the energy travels along the magnetic field lines. We have also some square dependence on the horizon angular velocity, and also this is to be expected, because of course, if the black hole is spinning, we do not extract energy. If the black hole is spinning fast, we extract more energy. And the square dependence is also very clear, because it doesn't really matter the orientation of which the black hole is spinning. So whether its spin is along the z direction or along the minus z direction, the magnetic field lines will spin accordingly, so that there must be some square dependence here. So this is the leading order term that was precisely obtained by Blanford-Znaeck, and it works quite well, actually. It is kind of surprising because this perturbative expansion seems to work quite well even when the black hole is in the almost at the high spin regime. Actually, what was found both numerically and analytically is that if we need to describe black holes which are close to the extreme limit, then we need to modify this formula by adding some correction. So here is the final formula that one expects for the Blanford-Znaeck power. Here there is some inconsistency in the notation, but I guess you can understand how they are related to each other. And in particular, we have some object, some prefactor which characterize the magnetic field topology. And this, in our case, is associated to a split monopole configuration. Then we have the dependence on the horizon magnetic flux, the square dependence which was originally predicted by Blanford-Znaeck, and then we have an I-order spin factor, which comes from pushing this perturbation theory to highest orders. And probably I will discuss about this in the afternoon. So this was everything that I had to say about black hole electrodynamics. Thank you very much.
Thank you, Filippo, for this very nice set of lectures. I believe we have time for a few questions. Carolina, please come here.
So, Filippo, I was thinking about, because with the more recent images of the black holes at the center of the two galaxies, we have now more information about the polarization of the fields. And so, how well does this constrain the characteristics of the electromagnetic field around the black hole?
You mean if there is some testing of the black? Like, you mean if there is some testing of the Blanford-Znaeck mechanism by means of these images? Yeah. Okay. So, what they do typically in the Event Horizon Telescope collaboration is that they capture the image, and then in order to interpret the black hole parameters and also the plasma parameters, the environment, they run a huge number of magnetohydrodynamical simulations. And then they try to understand what is the simulation that best fit this image. Now, if you look at the first papers that discussed M87, the image of M87, at some point say that only those simulations which are characterized by a Blanford-Znaeck process active can fit these images. Now, there is no precise understanding of the power emitted in the jet, like the measurements are still very uncertain, but the hope is that they will refine the measurement as much as possible so that we can also use the Blanford-Znaeck formula that I showed you before to constrain the spin of the black hole, for instance.
Thank you.
Thank you.
Okay, further questions? No one seems to have a question at the moment. I have a question. So, it's a curiosity really, I mean, but you showed us the equations for the force field for electrodynamics, right?
Yeah.
And as you pointed out, you could face it on a theory of its own.
Yeah.
In fact, a nonlinear theory of electrodynamics.
Yeah, absolutely.
So then you have the field equations, the Bianchi identity, and we could neglect for this purpose the currents. But anyway, so what I was wondering, and also making contact with the course by Anna, so is there a Lagrangian for this model?
Yeah, there is a Lagrangian. I think, I don't remember precisely how the action takes its form. At least I remember in terms of the field variables that I showed you before. But I think that the Lagrangian is some sort of like the standard electrodynamic Lagrangian with some additional Lagrange multiplier that impose the force-free constraint here.
Yeah, but I was thinking more just taking at face value those equations of motion, F rho nu, covariant nu, F mu nu, and the Bianchi identity, which doesn't really matter if we formulate the Lagrangian in terms of the field strength.
Yeah.
Would there be, without Lagrange multipliers, such a Lagrangian, a relativistic Lagrangian, just a function of the relativistic invariance that would give us this equation of motion?
I think that the answer is yes. I don't know the exact form of the Lagrangian, but I don't see why it shouldn't be. And of course, I think I'm trying to anticipate your idea, but of course, like if there is a Lagrangian, you can put it together with the Einstein-Hilbert action.
Indeed, I mean, but all of the theory related to nonlinear electrodynamics models, I mean, probably some people have thought about this, but I'm just curious, you know, could be applied, because this, for instance, you could consider it in flat space-time. You don't need to go to curved space-time. And there are some interesting properties, perhaps some interesting solutions.
Yeah, like for instance, pulsar magnetospheres in first approximation, of course, because it's anyway a neutral star, so it has a self-gravity. But pulsar magnetospheres are always like considered to be a solution of these equations in flat space-time. And you also typically consider a split monopole solution. You just have to incline it compared to the rotational axis of the star in order to generate the pulsar, you know, the thing that you showed yesterday of the pulsar rotation. Yeah. And there should be a Lagrangian. I don't know what it is.
I was even interested in more basic questions such as how would the Coulomb solution look in such a theory?
The Coulomb solution?
Just the Coulomb solution, because this would be a nonlinear theory of electrodynamics, right?
Yeah, but I mean the Coulomb solution
will remain as a solution because of just the first term, perhaps.
But you mean the electric?
Just the electric, yes, of course.
Yeah, but that's the problem, because you don't want electric fields if they are not screened.
But again, I think you were thinking about the context where this comes from, right?
Yeah.
But I'm thinking at face value, that theory over there.
I see what you mean. Yeah. Okay.
Yeah. So I forget about all of the context, and I just need. So what properties does this model have? You know, but I think it's going to be a solution just because you have the same term that you have in usual Maxwell theory. It's just contracted, then we get, but that will be zero for the usual Coulomb solution. So that would be trivially satisfied. But there could be something else, actually, that could be. But it's very nice. I mean, it comes from this context, but you get something that you could analyze per se. That's
And in recent years, there was a huge interest in force-free electrodynamics. Also, I had maybe some additional slide here. Like, oh, wait, I have to unskip it. There were kind of different formulations. So the one that I tried to follow is this space-time approach, which uses intensively differential forms. as I told you before, you can construct the theory in terms of foliations of the space-time, which is kind of quite intriguing and makes some contact, for instance, also with string theory in a sense, because you can consider these magnetic field lines as one-dimensional objects. And also recently, there was some idea concerning an effective field theory of force-free electrodynamics in terms of a cold string fluid. So you have that the magnetic fields are can be considered one-dimensional objects. You have some charge which is preserved by means of the Bianchi density, which you interpret as a sort of conservation law for a one-form global symmetry. And that leads you to a hydrodynamical theory of these fluids, which is cold because you want to keep it at zero temperature. If you keep it at finite temperature, you get magnetohydrodynamics. So yeah, there is a lot of interesting thing going on.
It branches off in many directions, apparently.
Yeah.
Okay, so we still have time for one final question. I don't think that people are interested, so... Well, they are interested, but not in asking a question. So let's thank Filippo again for his nice session.